So this is the Waves Homework Booklet question 32. We've got a narrow beam of monochromatic red light directed at a double slit. Parallel red and dark fringes are seen at the screen shown on the diagram above. Light passing through each slit spreads out. The name for that effect, very straightforwardly, diffraction, for spreading out when we pass through a gap. We're asked to then explain the formation of the fringes on the screen. So we've got light travelling from the slits where it's spreading out in all directions, and from each of the two slits, and how come we form fringes on that screen there. The overview is that we've got fringes forming by interference where the light from the two slits is overlapping, superposing. Now, to really explain that, which is what the questions asked us to do, we really need to be talking about the different sorts of interference giving us maxima and minima. So we're going to get maxima where we've got constructive interference, where the light waves meet in phase and reinforce. So that's the brightness. That's going to happen when we've got a path difference of n lambda. So the best answers would be linking a path difference of a whole number of wavelengths, giving us waves arriving in phase and therefore constructive interference, leading to a bright fringe. And then to go with that, we're going to get dark fringes where we've got destructive interference going on. What's going to lead to destructive interference is that the waves arriving with a phase difference of 180 degrees, pi radians, and that will occur when we've got a whole number of wavelengths plus a half. So half a wavelength, 1.5 wavelength, 2.5 wavelength. The other requirement we need for that interference to happen is for the light from those two slits to be coherent. Otherwise we don't get the linking between the path difference and the phase difference. So we need to, in your answer there, to be linking path differences to phase differences to constructive or destructive interference, and therefore the brightness or the darkness. Lots of things you could say there. You only needed to hit on 4 of those. Slit spacing was 0.56 millimeters. Distance across 4 fringe spaces was 3.6 millimeters, and the screen was at a distance of 0.8 meters. And we've got to calculate the wavelength. Lambda Ws upon d is, I think, the form of the equation on the formula booklet. So first thing we need to do is to calculate W. What we've been given here is 4W. It's the distance across 4 fringe spacings, not from 1 to the 4th, which would only be 3 spacings, but 4 spacings. So we've got 3.6 millimeters divided by 4. So I reckon we have got 2 significant figures there. So 0.9 times 10 to the minus 3 meters. Then it is just a case of lobbing that in. We've got to make sure we've got our minus 3 for the millimeters, minus 3 for the millimeters, and that comes through to 630 nanometers, 6.3 times 10 to the minus 7 meters. So essentially pretty straightforward use of that equation, with the little twist that we had to work out what W was. How would the appearance of the fringes change if how it would differ if we'd use white light? So if we're describing, we're not trying to explain anything now, it is just to describe what we get if we had white light. Now the central fringe occurs because we've got 0 path difference. Now 0 path difference will be 0 wavelengths, whatever the wavelength. So we still get a central bright fringe, which would be white. Now the point about white light, of course, is that it's made up of a mixture of different wavelengths. So the maxima, or the maxima, will appear at different points for the different colours in there. So either side of that, the fringes are going to be spectra. And little detail is that it's going to be blue with the shortest wavelength, the shortest W. That's going to be on the side nearest the centre. As we get further away from the centre, those fringes might merge, they might well overlap. And in fact, a couple of little details. We've got, because red light has got a larger wavelength than the average of the white light, the fringe is going to be closer together once we swap to white light, and we're going to get wider bright fringes because of that range of wavelengths. Only needed to pick up 3 of those. I think the central, the crucial things that I would have expected you to pick up. The central bright fringe would be white. We get spectra either side of that. As we move further away from the spectra, from the centre, those fringes will merge. So that was the Waves homework booklet question 32.